Okay, now we have proved the Borel Cantelli lemma. And let's go back to the problem that motivates our theory. Although you might be able to see immediately from the Borel Cantelli lemma that the probability that you get a 6 infinite often when you throw a die for infinite many times. Let us still make this problem more formal and rigorous. Specifically, let us try to construct a probability space that models this problem in a formal way. So for the dice throwing example, so you know a die has 6 sides, and let us denote it by a set of integers from 1 through 6. You're going to throw this die infinite often, so let's take an infinite product of this 6-element set. And this will be our space. On this infinite product space, the Borel sigma algebra, let's use script A, will be, do you remember? For an infinite product space, the product sigma algebra will be the Borel sigma algebra on this infinite product space, where we consider the finite set of integers 1 through 6 to be a discrete space. So you consider the power set of a set of integers 1 through 6. And you consider the product sigma algebra. This sigma algebra is generated by the cylinder sets, where each cylinder set is an infinite product where only finitely many of members or factors can be non-trivial. So for each cylinder set, you will get a set like this. So you get A1, A2 through AN, and all the rest are the full spaces. The sets A1 through AN are subsets of 1 through 6, which are not necessarily the whole space, but all the rest are the full space. So those sets are called the cylinder sets. And this sigma algebra is generated by those cylinder sets. Okay, now you have the space and the sigma algebra. Then what is the probability? The probability is a product of the probabilities on this space of 6 elements. What you are going to do, formally, you're going to take the sum of the Dirac measures denoted by delta sub E, and you normalize it by multiplying it with 1 over 6. You take the sum for E ranges over 1 through 6. That is your probability on this finite space, which exactly models the die throwing for each time. Next, what I'm going to do is that you raise this to a product, and this product is defined also on those cylinder sets, and use the measure extension to extend it to the whole space. So what we do is that the probability of those cylinder sets are said to be this product. And once you have this, we know that the probability on this infinite product space is uniquely defined through the definition of P on those cylinder sets by measure theory. I talked about this in another video on Bernoulli shifts in my video series for ergodic theory. You might want to take a look. Okay, now we have constructed the probability space. Our next goal will be to construct the events A sub n's. So what will be A sub n's? A sub n will be the event, so where the point is taken from the sample space. So this is an infinite vector, where the nth component of this infinite vector is equal to 6. Specifically, it means, so concretely, this means at the nth time, when you throw a die, you get a 6. So this means you get a 6 at the nth time. And now you take the limb soup of this. Remember, this is the intersection of union A sub n's, n equal to capital N to infinity, capital N equal to 1 to infinity. And this is the event that you will get 6 infinite often. So now we are ready to apply the Borel Cantelli lemma. So first, notice that those A sub n's are independent. You can get the independence immediately from an intuition, or you can check it formally. So what you do is that, sorry, I made a mistake earlier about notations. I'm supposed to use different notations. So I use the A sub n's in different places where they should have different meanings. So I should put tilde here. This A sub n tilde is just a subset of 1 through 6. But this A sub n is an infinite product. So now, to check the independence of those A sub n's, so take A sub n1 intersection A sub n2 intersection all the way through A sub nk, where n1, n2 through nk are distinct. And you know the intersection of them look like this. You will get 6 somewhere in k different places. I just wrote 3 places, but you should know there are k places where you should see those 6. And in between and beyond, you will see this full set, 1 through 6. There are infinite many 1 through 6. All but finite many of factors are 1 through 6. And you take the probability of this, what would you get? what you get is the product of k many 1/6. So this k many, which will be equal to the product of those individual guys. And this verifies the independence of A sub n's. And furthermore, you will see immediately that if you take the sum of probabilities of those guys, you get the sum of 1/6, infinite many, which is infinity. Then it follows from the Borel Cantelli lemma that you get the probability of the slim subset is equal to 1. Namely, with probability 1, you will get 6 infinitely often. And that completes this example.